Alright, so we have our image, it's focused, beams aligned, everything's done. So now we can go over to doing the EDS, but let's go back and make our spot size a bit bigger so we can get a bit more signal. Alright, so we go to the chamber view. So on the EVO image, the EDS computer now, you guys can all see that?
Yeah.
And we go and open up AZtec. And we create a new project. Remember, always saving our data in the EDS data folder under our name or uni key, and select a project name. Go back to our EVO, the SEM computer, and we make sure that the EDS detector is not going to hit anything. Yep, so we're all clear. And then we click on our icon in the bottom. And position and in. And if we go over to the SEM computer, we can see the detector moving in. And we're at that working distance around 17 millimeters, so we should get a good signal. We can see that we're getting too big a dead time here, and that we remember that's because we still have the chamber scope on in the SEM computer. So we've got to remember to make sure we turn that back to our detector of choice, either the SE2 or the backscatter detector, so that we turn off that infrared camera. And now we can see our dead time and our input count rate is within our operational specifications. We always want to be that in between 20 and 40% or 20 and 50% for our dead time, so that's pretty good right now. Remember, we can always change if we want to have our processing time, we can change it between, say, 2 and 5 if we want to increase our dead time. So if we want more accurate results and allow it to process that signal for longer, we can change the processing time. So depending on our input count rate as to how much processing time we can handle. Obviously, the more signals we get, then the dead time will go up higher for any given processing time. We can choose any predefined elements. I recommend, unless you know specifically what you're looking for. In this case, we know that we're looking at gold, so we'll add that in for sure. By double-clicking, it can turn green, but we'll also perform auto ID for it to find any other elements that we are unsure about. We always want to work in a workflow way, so we always start with what kind of data we want to collect, whether it's mapping, point and ID, line scan. So let's start at point and ID again. All right. The summary is where we can add in So we start with the point ID and we go to the next flow, describe specimen. And this is where we can add notes to the specific specimen or the specific site. We can right-click and rename the specimen. We can also right-click and rename the site. Obviously, we can add new specimens if we're moving to different specimens, and as we go to new areas, we can add new sites for the same specimen. So we go across the workflow and go to the next step, which is scan image. In this scan image area is where we can add new sites. You can also navigate all of the sites and specimens in this data tree tab on the right-hand side. In the Scan Image tab, we have the option for settings and to choose the resolution, the dwell time, and if we want to put auto lock on, which is a drift correction. The input signal here doesn't matter. We should always make sure that there's a tick for the SE, but it will only ever take whatever signal is selected in our SEM control. So whatever signal we chose when we were collecting or when we have on the SEM computer is what will be collected. 1000 image is always good for training, but you guys can choose as high resolution image as you want. Just remember that the more pixels, it'll take you a lot longer. For backscatter detectors, you want to go a little bit longer dwell time because typically they don't have as much signal, so you want to get rid of the signal to noise. Right now we're using the secondary electron detector, so we can just leave it at that. When we're doing point and ID, there's no real need to use the drift correction because typically it's you're not on the same site for as long, and if your pixel is to move a few, it's not such a big deal. Whereas in a map, if your image drifts at all, then the map will blur out basically because each time it collects more data, it's slowly drifting left or right, or it's drifting more and more, and so it's like when you were to take a camera image and something's moving in your camera image and the image blurs out. So because it's such a slow capture time when we're doing mapping. So let's collect our image by clicking Start. There's our secondary electron image coming in. After we've done this step, we can go to our next in the flow, which is acquiring the spectra. Now this simply means just collecting a X-ray spectra for any area or point that we want from our secondary electron image. On the left side, we can choose a single point. We can collect the spectrum from a rectangular region, a circular region, or you can free draw. So if you want to collect it from an odd shape. I'll show you a few different options. Regardless of what area you're collecting the spectrum from, though, we have to choose how long we want to collect it for. We always want to leave the energy range on auto, the number of channels on auto, and the process time should be what we selected here in order to get our adequate dead time. So in this case, we selected 4 because that gave us our dead time of 25%. At this input count rate. The different acquisition modes, I always recommend doing live time. You can do it by counts. I don't recommend doing auto. The live time is just easier when you want to calculate how long you're going to be actually waiting around for. But it's only good from on the same sample. If you're moving between different samples or wanting to compare absolute counts between samples, then that's when you might use counts. But for 99% of the time, live time is fine. For training, we'll do a 20-second live time because we just want to do it a bit quicker. Because whenever we take this live time, we have to take into consideration the dead time. So this will extend out by 20 to 30% based on your dead time. I'd recommend doing around 50 seconds though to get a nice smooth graph, but it really comes down to the peak to background noise you're looking for. So if you're looking for very small trace amounts, then you'll need to have longer position times. So let's collect a single spectrum from this point. Let's do a freehand draw spectrum from around this grain here. So we can average out the spectrum across that whole area. And let's do a square one from here. And we might as well collect one from the black region as well. So I've selected all these different regions and it will go through one by one and in the order we did it, collecting the spectrum. And you can see those spectrums coming in here, and as it starts off it's quite a noisy signal. As it keeps counting, that signal gets smoother and smoother as we get a better signal to noise. And if you wanted to try and identify some of these smaller peaks, that's where you might need to do a longer counting time. One thing to always remember is that if you know what elements you want to use, and you know what peak you're trying to identify, you always want to select a voltage on the SEM that's twice the accelerating voltage of the energy of the X-rays you're trying to excite. So in this case, gold at say around 10, being at 20 kV means that we're going to be able to excite that fine. But you can see how the background really tapers off at that 20 kV energy range. So that's why we always want to be at double, that we know that we're exciting enough of those X-rays. And now we've collected all our spectrums. So we can, at any point, we could have gone to any of these spectrums and gone to confirm elements. And that's where it tries to do some fitting for the elements that it's identified. If we're unsure that there might be another peak or another element there, see, it's fitting for these humps already. So it's taking into account all of those energies. The one thing that it's trying to do is fit this copper here. And see, we're missing a large amount of copper, but when it's doing that's in the theoretical spectrum, but when it does a fit, it's able to actually smooth that out and realize that it's just in the background. The small amount of copper that we're actually having. When we start to look at those, see how the gold though is much lower. So this is where we might have to start to take into consideration that this is not a very accurate fit, and that's probably because this is a thin film. So it's, when it's doing all of these calculations, it's assuming a bulk specimen, and we're working on a thin film. So whenever you guys are working with very small particles or rough surfaces and things, that's where you can't take the accuracy of these values. You have to take into consideration other effects. So just always be aware of that it's not a black box. You can't just stick your sample in, press go, and get a number and just always quote that number. You have to use a little bit of knowledge and understanding of how that signal is being generated and where you can generate errors.